So today we're going to be looking at concepts of light and boundaries. How does light reflect off of surfaces, and how does light travel through surfaces? So we're going to be taking a look at concepts of reflection, and we're also going to be taking a look at the bending of light that takes place inside different materials, and that, of course, is called refraction. So this is section 17.1. So let's imagine that you have a black surface. This is some background information. And you have the sunlight that's coming in, or any type of light source that is coming in. Okay, of course, if you're wearing a black shirt on a sunny day, that black shirt has pigments in it that absorb the energy from the light. So the energy that's coming in, a lot of it gets absorbed, and what happens is we get, some of that could be reflected, but not a lot is going to be reflected. If you have a white surface that lacks pigments, the energy is going to be coming in, and a lot of that is going to be reflected back. So the question is all of it reflected back? And the answer is no. The reason why is because there are still molecules that are inside this white surface, be it a whiteboard or a white shirt, and those molecules can still absorb some of the energy. Most of it, yes, is reflected. So we've got some that is going to be reflected back with the black surface. We have most of that light that's going to be reflected. Well, how about a mirror? If I have a mirror, what's going to happen here? The energy is going to come back, or come in, rather. So here's the energy. Are we going to get 100% of the molecules coming out? And the answer to that is no. So here's a mirror right here, and this mirror actually has silver molecules. One of the activities that we do in normal physics class is we make a mirror, and we see that there's this plating process, and it uses silver. Silver is an atom. This atom is complex to a molecule. That molecule actually absorbs light. And so even with a mirror, what we get is we get about 90% of the light that is reflected. And we can see this if you have multiple mirrors and reflect off of multiple mirrors. The intensity of the original light gets diminished every mirror that you use. So let's take a look at what's called a regular reflection and a diffuse reflection. So I'm going to dim the lights down. Here's a regular reflection. I have a laser here. Here's the mirror, and when I take this and put it down, we have, again, the regular reflection. So the regular reflection means that it's going to be coming off the same angle that it is coming in. So that is a regular reflection. So regular reflection occurs, of course, with a mirror. So a regular reflection, this is when you have a smooth surface. What's happening is with this pointer and the laser coming in, this is not just one photon of light that's coming in. It's actually multiple photons of light that are coming in. They're coming in parallel. So they're coming in parallel like this. And what's going to happen is these are going to then leave, and they'll also come out parallel. So with a smooth surface, these rays of light are coming in, these rays of light are going to leave. We've talked about this before in a previous chapter. We have this concept of what's called a normal. And angles are measured with respect to the normal, not with respect to the surface. So this is a 90-degree angle here. That's the normal. And let's say that this angle that's coming in is 35 degrees. If this angle coming in is 35 degrees, if this is a reflection, the angle going out is going to be also at 35 degrees. That would be the definition of a reflection. So now I have a material aluminum foil. How does the laser pointer reflect off of this? So here's the light coming in. And you can see it's not exiting at the same angle. Okay, why is it not exiting at the same angle? It's because this is not a smooth surface. So this is called a diffuse reflection. Diffuse reflection. And if you've got a rough surface like this, and if you have some parallel rays that are coming in like this, and you have this parallel ray coming in like that, this might reflect that way, and that might reflect that way. So with a rough surface, you get what's called a diffuse reflection. So in reality, the reflection's always going to be occurring at the same angle that it comes in. When it's smooth, it exits the same angle. Well, what's going to happen is it depends upon the angle that we're coming in with each of these miniature surfaces. So this is actually a regular reflection for this one beam of light. This is a regular reflection for this because it's coming off at the same angle that's coming in. However, it's a rough surface, so they're going to be hitting different angled surfaces, and so they will exit at different angles. So I remind you guys about refraction. So this is reflection, and let's take a look at refraction. If you remember, we discussed refraction a couple chapters ago. And imagine that you have a toy car, and you're driving it along a sidewalk, and you are in a construction area. They haven't finished the driveway yet, and so it comes upon this angled surface. Over here is mud. And what happens is this wheel is going to contact the mud first, and it's going to slow the vehicle down. So the velocity will be like this, but the velocity of the top wheel is still going to be going fast until it hits that right there. The net effect of this is it's going to turn the car into and toward the denser material. This is the concept of refraction. So with reflection, again, incident rays coming in and the exiting rays are going to be at the same angle. With refraction, we get a bending of the waves. The wave bends, okay? And it bends toward the denser material. And that's going to be an important concept. Wave bends towards the denser material. So what I'm going to do is I'm going to be bringing in now a material that is going to be denser than air, and it's going to be this little square piece of glass. What I'd like you to do is if you can get a ruler and if you can draw a nice square, and you're going to have to sort of trust me on this since you're not here. And there's also going to be a lab that's very, very similar to this where we're going to be calculating the angles. So here is my material, and I'm going to be sending in my beam of light. And we're going to be looking at the refraction. Now, if I send my beam of light coming in from the top and make it go straight through, there's not going to be any change in the angle where it travels through this glass material. However, when I shift this angle over here, what you should note first of all is we have a nice reflection on the top. We see a little bit reflecting, but then we have this beam that goes through the glass and then also exits the glass as well. So what I want to do is I'm going to try to make a line and show you how I'm doing this. Okay. I'm going to be making a dot at the point of the laser and where it is entering. Let's see if I can get this. Okay, there. So I'm going to put a point at the surface of this, and then I also have a reflected ray that's coming out, and then I also have a refracted ray coming out as well. So I'm going to be now turning on the lights, and we're going to draw all these, and I'd like you to draw them in a likewise manner. So I'm going to go ahead and get my ruler. So we have the incoming beam that looks like this. And we had a reflected beam that was coming off of it like that. So this is coming in, that's going out. But we also had the light that traveled from this point to this point through the glass material. Now let's do a couple things here. Let's go ahead and we'll create our normal. Our normal, again, is going to be parallel to the surface. I'm going to draw that as a dotted line. So this is the normal. We're going to name a couple of things here as well. So here's the normal. This beam of light coming in is called my incident ray. So it's the ray that's coming in. And since this is a reflection, this is going to be the reflected ray. So the incident ray coming in and the reflected ray going out. This creates an angle. This is going to be my angle as measured with theta of the incident angle. And we also have the reflected angle, lowercase r. Now what happens is, let's go ahead and extend this normal going down through the glass. And what you can see is this does not continue on its straight path. Okay, this would be the projected path if there was no glass there. But you can see that the light actually was shifted and it bent toward this line right here. It bent toward the normal. And that's going to be important as well. This is going to be my refracted angle. So, and it's going to be the first refracted angle. And then, well, if this were to continue on its path inside the glass, if I had a larger piece of glass, it would have ended up here. But it didn't. It actually bent back out like this. So since we have, we're coming into this material, this is the reflection. Here's my refracted angle. Here what happens is the ray is bent toward the normal. But now we're coming from the inside of the glass to the air again. We have to create another normal right here. Again, it was projected to exit right here if it was continuously being glass. However, it bent back out away from the normal. So here it bends toward the normal. Here it bends away from the normal. So this angle right here is going to be the second refracted angle. So let's take a look at the materials. This is made up of glass. This is much denser than the air. So here's the air. Here is the glass. So air is less dense. It is less dense in terms of mass and weight, but this is what we call optically dense. So it's less dense optically. So when we go into the denser material, what happens when we enter the denser? That's what we did right here. When we enter a denser material, this is the main point of this refraction. The light bent toward the normal. When you enter the denser, a couple things happen. Light bends toward the normal. Just like the car bent inward towards the mud. The light bends toward the normal. What this will mean as well is your angle of incidence, which is right here, your angle of incidence is going to be greater than the angle of refraction, the first angle of refraction. So right here, this is going to be your refracted ray. And we use a capital R for that. Then note down here, when the light exited the glass, it's now entering air, which is less dense. So when you enter less dense material, okay, the light bends away from the normal. Light bends away from the normal. And what that means is that your refracted angle here is going to be greater than the refracted angle on the inside of the glass. Can you guess the significance of this right here and this right here? Well, if the light's coming in from the air and it bends inward because of the material, and then it's going to bend outward, it's bending outward into the same material. Can you guess the significance of these two angles? What we have here is, in theory, the incident angle should be equal to your second refracted angle, because it's the properties of the glass that's bending it inward, and it's the properties of the air that are bending it back outward, back to its normal angle. And they sort of look a lot like each other. And we'll do a lab where we'll actually measure these. So we're going to now take a look at something that's called Snell's law, that's beautifully trigonometrically formulas that can predict what these angles will be based upon the properties of the optical density. So this is called Snell's law. And for Snell's law, we need to know what's called the index of refraction. So N is called the index of refraction. If you have glasses or contacts and you go in for a prescription, the prescription that the optometrist fills out is called a refraction. That's what they will also call the when you're going in to have your eyes checked, and it's a refraction. What they're doing is they're bending the light. They're bending the light inside of your glasses or your contact because it's not bending properly on the inside of your eye. So they're changing that. So the index of refraction, how much refraction are we going to be getting? So this tells how optical dense it is, tells how optically dense a material is, and it also tells how much the light's going to bend. Tells how much light will bend. So the higher that your number is, the more dense it is, and the more it's going to bend the light. So here's Snell's law. It's very simple. The index of refraction of the incoming or incident material that was the air in our previous example, times the sine of the incident angle will equal the index of refraction for the refracted material times the sine of the angle. So again, this is your incident, and this R is your refracted. So what's pretty simple is that the index of refraction of air and also the index of refraction of a vacuum are very, very close to each other. It's actually 1.00. So even though we have lots of particles that are in the air, it's actually 1.000000, and then it's another number. But it's very, very minimal, so it's just assumed that air in a vacuum, the index of refraction is going to be 1.00. So let's say that we have an angle coming in. So we have a piece of glass, and we have our angle coming in at 60 degrees. Okay, and remember we measure it from the normal. Okay, so it's coming in at 60 degrees. So we can just do a quick sketch of this over here. Okay, so remember we measure from the normal. So 60 degrees is coming in like this. So that's the 60 degrees, and it's going to be refracted at 40. So remember, it's going to be, in this case, it's going to be optically denser, so because we have a lower angle. So since it's a lower angle, it's going to be bending toward the normal. And let's go ahead and label these. The index of, the angle of incidence is going to be equal to 60 degrees, and the angle of refraction is going to be equal to 40 degrees. The question is, what is going to be the index of refraction for this material on the inside here? That's where we use Snell's law and we rearrange. So let's go ahead and plug in this formula. We have the index of refraction for air, because that's my incident. We're coming in from the air. We're going into this unknown material. So times the sine of theta is equal to nr times the sine of theta r. So the index of refraction coming in from the air is 1.00. Okay, we're multiplying it by 1. That's not going to change any value. Times the sine of this angle of incidence, which is 60 degrees, is equal to the index of refraction. And we actually need to divide both sides by the sine of this to get to this all by itself. So if I divide by the sine of the refracted angle, it's the sine of 40. Now when you do this, make sure that your calculators are on degrees, not radians. So we have to use degrees on your calculator. So let's make sure that we are on degrees. Okay, I'm on degrees, and I can go ahead and do this problem now. So I have 1.0, but actually that's not going to affect the problem at all. So it's really the sine of 60, enter, divided by the sine of 40. And that will give me 1.35. So the index of refraction for my material is 1.35. And of course, it's more than 1.0. And when we increase the index of refraction, it's going to be optically denser. And when we decrease the index of refraction, it's going to be less dense. So this is using Snell's law. Here's the master formula. And this was used to find the index of refraction. But we might actually be given the index of refraction, and you need to calculate what is the angle going to be if we know this material. Okay, so let's take a look. Imagine that we're coming in from air. So I'm just going to do a quick sketch of this. Okay, we're coming in from air. We're going into this material, and I think it's going to be glass, just like it is, right here. So this material is going to be, the index of refraction is going to be equal to 1.52. So of course it's much denser than air is. Okay, we're going to also be coming in at a 60-degree angle. So we're coming in at a 60-degree angle. We can actually predict what it's going to be compared to this. This had an index of refraction of 1.35, and it bent it to the angle of 40 degrees. So now that we have a larger index of refraction, can you guess what's going to happen to the refracted angle? If you increase the index of refraction and you have a denser material, it's going to bend it even more. Okay, so if you higher index of refraction, it's going to be denser, it's going to bend the light more. So that's what we can expect. So in the previous example, it went in at 60, it came in at 40, so we should be looking for an answer that is less than 40. Okay, let's go ahead and we have the air. The index of refraction of air is equal to 1.00, and we are trying to find what the angle is going to be. So we want to know what is the refracted angle. So we're going to use Snell's law times the sine of the incoming angle is equal to index of refraction times the sine of the refracted angle. We're trying to solve for this, so we're going to divide both sides by the index of refraction for the refracted material, index of refraction for the refracted material. Those will then cancel. I'm going to just put this on the other side. So the sine of the refracted angle is going to be equal to, I'm going to plug in some numbers. The index of refraction for the incident angle is coming from air, so it's 1.00 times the sine of the incident angle, which is 60, divided by the index of refraction of our glassy material, which is going to be 1.52. That will not affect this. So now what I do is I'm going to be having the sine of 60 divided by 1.52. Now, this answer gives me 0.5697, but I'm not looking for that. This is the sine of the angle. So at this point in time, what I need to do is I need to do the inverse sine of both sides. So all of this needs to be the inverse sine. So I'm going to be doing second shift sine, and then I'm going to be plugging in second shift my answer, and that will tell me that it was 34.7. So my refracted angle is going to be 34.7 degrees, and we had a higher index of refraction. It was denser. In the previous example, it came out at 40. This came out at 34.7 degrees, so it bent even more toward the normal. What's interesting is that the index of refraction not only affects the angle that it bends, it not only tells you how optically dense it is, but it also tells you how fast the speed of light will travel. So the speed of light is considered to be a constant. Well, it's considered to be a constant inside a vacuum where there are no particles to affect its velocity. However, the speed of light travels differently inside of a vacuum compared to a piece of glass. So the speed of light is traveling differently here, and the speed of light is traveling differently on the inside of this glassy material. We can calculate that velocity with this formula here. The index of refraction of a substance, and I'm just putting this here because we have many different substances that we can test. We have quartz, we have diamond, we have cobalt, we have many different things that we could send light through. We have water as well, is equal to the speed of light divided by the velocity of the light in that substance. course, the speed of light is equal to 3.00 times 10 to the 8th meters per second. Now, imagine we're going through a vacuum. A vacuum is 1.00. So if it's 1.00, the velocity of light in a vacuum is going to be the same as the speed of light, because the same number divided by the same number is going to be equal to 1. However, there are many more substances that do not have a index of refraction of 1. Most substances actually have higher indexes of refraction. What's going to happen is, well, the velocity can never exceed the speed of light, but you can see what's going to happen. What's going to happen to the velocity of light in that substance? It's going to decrease. So in all the materials except for a vacuum and for air, you're going to have a higher index of refraction, and your velocity is going to decrease inside that substance. That's it for now.